Welcome to the next video in a course in discrete math. This is lesson 5, discussing propositional variables and truth tables. In this video, we will see what a propositional variable is, propositional operations, and truth tables, examples, and exercises. Now, to motivate the use of propositional variables, we have so far only looked at examples of particular propositions, but logic is about propositions generally and how to work with them and reason about them. So we should try to abstract away all of the details that we don't need for any particular propositions and instead work with propositions more generally, keeping only the features that should matter for logic. So instead of giving an example like she went to work or the store, we'll instead write P and then this disjunction symbol Q. So P and Q are propositional variables, and they will stand in place of arbitrary propositions. So she should have been went to work. She went to work. P would stand in place of that proposition, and then she went to the store. Q would stand in place of that proposition. And they are joined together with the word or, well, when we are being symbolic, right, when we are abstracting these propositions into propositional variables, then we'll use this sort of downward wedge to represent or, and that is the inclusive disjunction. So these are what we call propositional operators. So if you take any proposition and you apply one of the symbols, so this would be for negation, right? This would represent not P. And so this is called a propositional operator, the not symbol, because from a proposition, you apply the operator, you get a new proposition. Likewise, conjunction, that stands in place of and. Disjunction, we've already talked about. Exclusive disjunction, and so on. You can use each of these to form a new proposition. And in fact, you can make increasingly complex new propositions by stacking the operators higher and higher. So let's see another example of going from a specific proposition to its abstract symbolic form. So we could take this proposition, if the triangle is not a right triangle, then. Now already we can say that this is going to be a conditional sentence, right? The main structure of the proposition is conditional, and the antecedent is that the triangle is not a right triangle. So just on the spot, I'm going to make up R to be my symbol. It is a propositional variable. It is meant to abstractly represent any proposition, but as it relates to this specific instance, R will be the symbol for the triangle is a right triangle, and so I'm putting here the negation of that in the antecedent of the conditional. And then we can say then either it is, again, a typo, either it is acute or obtuse. And so here, I think context would suggest that we mean the exclusive or when we say that. And so I make up another symbol for acute, another symbol for obtuse, and I join them together with the exclusive or operator. And notice the use of parentheses here to make sure that it is clear what order these are supposed to be read in. So by putting the parentheses around the R, or the negation R, we are distinguishing this from the very different sentence, if R then A O plus O. So this is a very different sentence, but if you didn't have any parentheses telling you which way to read it, then you would have written it as negation R, arrow, A, O plus O. And you wouldn't have any way of knowing which one this was supposed to mean. So the parentheses here are to make this explicit. So moving on to another example, this number cannot both be even and odd. And again, the parentheses matter here, so I am writing the negation on the outside of the claim, O and E. This time O means the number is odd and E means the number is even. I swapped them around, but that shouldn't really matter. Now, as we've been discussing, when we make these propositional variables and we start writing down propositions, we can make these propositions as arbitrarily complicated as we want. I mean, you could have the proposition, negation, P, conjunction, negation, Q, conditional, Q, biconditional, P, O plus Q. Anyway, so the point is, very complex propositions. And as they get more complex, it is harder and harder to reason about their truth value in any given scenario. P may be true, Q may be true, or each may be false, right? And so, figuring out, would this proposition be a true proposition when P and Q are both true? Or what about when P is true and Q is false? And so on, right? So that gets increasingly complicated as the proposition becomes more complicated. And so what we're going to do is introduce this notion of a truth table as a tool for managing the complexity of determining these truth values as propositions grow more complicated. The most basic truth table is very simple, so simple as to seem kind of needless. But again, when the proposition is simple, you don't really need truth tables. It's when they get complicated that you need truth tables. But just starting at the simplest example, then you could have a single propositional variable, and this expresses that it may be true or false. And that is the truth table, right? A row for each scenario about whether P could be true or false. We start to appreciate what a truth table is doing when we see the truth table for negation P. So this is the truth table for negation P. We always start off writing the propositional variable and listing its possible values, which are true or false. But now as the proposition gets more complicated, we use those values to compute the values, the corresponding values for the negation. Now, remember, the rule for negation is that whenever the proposition is true, then the negation is false. Whenever the proposition is false, the negation is true. So this is the truth table for negation P. Here we move on to truth tables for the binary operations. Right, the negation is a unary operation. It applies to only one propositional variable. These are binary operations because they apply to two variables. And we now have to consider four possibilities. So there's when both are true. P is true and Q is false. P is false, Q is true. Both are false. Each of these is now a possibility that's going to affect the truth value of the proposition. When it's conjunction, we get truth only in this first row and not in any of the other rows. When it's disjunction, we get truth everywhere except at the last row. So it is only false in the last row. And then when it comes to exclusive disjunction, we get false on the first and last, but true everywhere else. So there are the truth tables for these operators. And the final two operators that we will study are the conditional and biconditional. And you can see their truth tables here. Worth noting that the conditional is false only at row 2, true everywhere else. And then the biconditional is true at the first and fourth, false everywhere else. Now let's see ever increasingly complicated truth tables. And so we'll look at the proposition negation on the outside of P conjunction Q. Now, the way that we form the truth table here is we first form the truth table for the simplest sort of components. In a sense, the simplest possible components are just the variables. And as I said, we always start there at just the variables, running through all of their truth possibilities. They are standard, right? Like you kind of just always write those down as true, 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 false, false, true, false, false. That's just standard, right? You do that in just about every truth table that has two variables. But then you move on to the next most complicated part of the proposition. And in this case, the next most complicated part of the proposition is P and Q. So you do the truth table for that, and you use the previous values to help you compute it. So when you've got P over here and Q is true, right? So P is true, Q is true. Then you apply the rule for conjunction in the truth table for P conjunction Q. I'll go ahead and note, and I'll be using this later on as well, that you could kind of express what I'm doing here as saying that if you have true conjunction true, right? Just, instead of, talking about P, we'll just use T, because in this scenario, we are imagining that P is true. And likewise, we're replacing Q with T because in this scenario, Q is true. And then we'll just say that the conjunction rule is that true conjunction true is true. If we sort of apply the same system to the second row, then we would say that we're looking at true conjunction false, and using the conjunction rules, this evaluates to false. So that's why that coordinate gets an F. And likewise, and so on, you just kind of compute what we've already done, I guess maybe a couple times now, the truth table for the conjunction. But then you move on, right? Like once you're done with that, the simpler components, you move on to the next most complicated component. And in this case, that's just the very final component, which is the negation on the outside of that. And this time we kind of do it all over again, but make sure that when you're computing the negation, you're computing the negation of this. You look up its values in the previous column of the table. So here we're going to compute negation F, which is true, right? Negation true, which is F. And in the second row, well, actually, I guess I should start indicating here. In the second row, this is going to be computed by taking negation F, right, where F is taken from the previous column. So negation F evaluates to true. And so that's why we get true here, and so on through the rest of the table. I think that's probably pretty clear, so I'm going to move on. Now, we've just done a specific example, and I want to just generalize, make sure that you kind of get the general procedure, right? So how do you make the truth table in general? First, you identify all of the propositional variables. And the number of propositional variables will tell you the number of rows of the table. If there is one variable, you need 2 rows of the table. If there are 2 variables, you will need 4 rows of the table. If there are 3 variables, you will need 8 rows. The pattern here is that it doubles every time. So although we will not often work with propositions that have many more variables, because the number of rows just grows so quickly, and then filling in these tables becomes a real chore. So we won't often use 4 or more variables, but when, in the few cases where we will, you can always determine how many rows you need by taking, so if it's 4, you're going to take the number of rows you needed for 3, right? Just one before. That was 8, and then double it. So what you're going to need, right, if you have 3 variables, then you're going to require 16 rows. If you have 4 variables, then you're going to require 16 rows, which is twice the number you needed for 3 variables. And then if you move on, then when you have 5 variables, you need twice that. So twice 16 is 32. Okay, once you've identified all of your variables and you've computed the number of rows that you're going to need, then you're going to make a column for each of the variables. And then you need to start filling in the truth values in each of those columns. Let's assume, just for some specificity, that we just have three variables, P, Q, and R. And I'm going to draw what we do in that scenario correspondingly. So let's look here and let's sort of, as we go through the recipe, let's also draw the table. So we've got three variables. That means we're going to need three columns for P, Q, and R. And I'm going to go ahead and label that P goes here, Q goes here, R goes here. We know that because there are three variables, we need 8 rows. So 1, 2, 3, 4, 5, 6, 7, 8. Now, the recipe, the algorithm to fill in the values underneath the variables is to take the first, here, that's the P column, and fill half of its rows. So that's going to mean 4 values. Fill 4 values, half of the rows with the value true, and fill the remaining half with false. So 4 trues, 4 falses in that order. Okay. Now we move on to the Q column. And for that, we start by considering only the rows where P was true. And in those rows, we fill half with true and half with false. So that's going to be true, true here, and half false. So false, false there. Then in the, the next component where P was false, we do it again. So we fill half of these with true and half with false. And finally, for the R column, we take the part where Q was true. So that's going to be here and also here. And in these components, we fill half with true, half with false. So that's going to be true, false, true, false. And then we do it again where Q was false. So that's going to get you true, false, true, false. Now, I've described it this way, somewhat hoping that it makes sense why we do things the way we do, right? By filling it half true, half false, you've got both scenarios for P. And then inside of that, you've got both scenarios for Q, right? So where P is true, you also have the scenario where Q is true, and then the scenario where R is true. But then you could also say P is true in this whole region, and Q is true and R is false. So that's another of your various combinations of true and false for P, Q, and R. And so basically this section of the truth table gives you all of the possibilities when P is true, leaving that Q could be true and R true, Q true, R false, Q false, R true, so on and so on. And then you do it all over again, but this time repeating everything where P is false. So in all of this region, you now have P is false, but again, you run through all of the other possibilities for Q and R, where you have P could be true, Q could be true or Q could be false, and R could be true or false within each of those scenarios. So anyway, that's kind of, I hoped that by sort of laying it out in this way, that it would, the logic of it would make sense. But there can be a somewhat simpler description now that we've gone through it once. When you're actually computing these, you can kind of just say that for PQR, that you'll just do a certain kind of alternation. So I think I've got, so if P is here, Q is here, R is here, you can just fill with true halfway, fill with false halfway, fill with true right, like a quarter of the way. then false a quarter, true a quarter, false a quarter. Then true an eighth, false an eighth, true an eighth, false an eighth, true an eighth, false an eighth, true an eighth, false an eighth. So you can kind of do it by like halves, quarters, eighths, and then this recipe kind of continues to work even when you have more variables. But okay, once you have finally made just the basic values for your simple variables, the next thing that you have to do is identify these smaller, simpler subformulas. And so in this example, the smaller, simpler subformula was P conjunction Q. And now I'm going to start calling that an order one subformula. And it's this notion of order. I'm just going to introduce it by example, and later on we'll make it formal. But I think, the example is easier and clearer to understand. This is order one because the left thing I'm going to call order zero, right? It's order zero because it involves no operations. And the right-hand thing is also order zero because it involves no operations. But keep in mind, I'm not just counting operations. You'll see that later. But since the left is order zero, the right is order zero. And here what we have is their conjunction. So it's like one step extra complicated. Then I call that order one. So it's got order zero on the left, order zero on the right. Therefore, the conjunction of them is order one step extra complicated. But let's see this in another and more complicated proposition. Well, what do we have here? So we have the variables P, Q, and R. But negation P, that's going to be an order one subformula because, right, again, the logic here is that if you look at negation P, P again has order zero. P all by itself is order zero. Negation P is one step extra complicated, so that's order one. Q or R, well, Q has order zero, R has order zero. Therefore, the disjunction has order one. Okay, then let's come to the conjunction, the main, right, the end of this process. And we're going to say, well, the left has order one, the right has order one. And here, technically, what I'm going to do is compute the maximum of the two orders, right? So if I take 1 and 1, their maximum is 1, right? That's the maximum between 1 and 1. And so whatever that maximum is, I add 1. So this is an order 2, right? Order 2 formula because the left is 1, the right is 1. I compute the max, I get 1, and then the extra operation makes it order 2. But anyway, the relevance that this has for constructing the truth table is that we first, in a sense, kind of what we do is we first construct the order 0, right? That's this PQR. So we actually are always starting by constructing the order 0 subformulas. We fill it in the way that we've already talked about. So I'll go ahead and, but I'm going to keep doing it with PQR. Yeah, and maybe I'll use this proposition to demonstrate. So true, 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 and so what is that? 2, 3, 4, 5, 6, 7, 8. Okay. Fill half with true, half with false, and so on. Okay. But now for the next column, we put any of the order 1 subformulas. So for instance, I could put negation P here. That's my first order 1 subformula. And I compute its truth values. So its truth values are going to be, well, I have to look up the P column, right? Because this is negation P, so I'm looking under the P column to get true. And so this is going to be negation true, which is equal to false. And that's actually the value entered in this cell of the column. And then for basically the same reasons, we're going to get false, false, false wherever P is true. We're going to get true, true, true wherever P is false. Right? The negation is true. Okay, next let's write the other order 1 subformula, and that's going to be Q disjunction R. And again, we want to compute the truth value of this. So in the first row, that's going to be true or true is true. So that's actually the value entered here in the table. And then in the next row, that's correct. In the next row, but keep in mind that I should be pulling always from the values of Q and R this time. So this time Q is true and R is false. So I'll compute T or F and get, true. Then F or T, so T, then F or F, so F, then T or T is T, T or F is T, F or T is T, F or F is F. And there's my order 1 subformula. Now, if there were more order 1 subformulas, you would have to continue doing all these computations for all of the order 1, order 1 subformulas. So there you have it. Okay, now let's continue. So here I give a talk through how you compute the truth values for the order 1 subformula. So actually, I guess we could just move on since I think I've already described this in the previous slide. But now we move on to the next order, right? So we're going to find all order 2 subformulas. So notice that in this example with P, right, the negation outside of P conjunction Q, that was order 1, and the negation of that is order 2. So we now move on to computing that truth value, which we've already seen before, so I won't repeat doing that now. But what I will do for a demonstration is I will repeat the example that we had been working on, this one right here. And notice that this, we also said, was an order 2 subformula. So again, that was because this was order 1, this is order 1. So the whole thing is now order 2. And again, remember that the computation there is take the max and add 1. Okay, now to compute this, we have to look up the column used for negation P, and so that was F. So we're computing F conjunction. Look up the value found in Q or R, that is T, so F and T is F. Now, again, right throughout, for the rest of this calculation, I'm basically going to be using these 2 values. So I'm going to just compute the and between those 2 values, and they're going to come out false, 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 true, 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 and then false. And to compute truth tables for even bigger, more complicated propositions, of course, the suggestion is you go from the order 0 to the order 1 to the order 2 to the order 3 and so on. And you do this until eventually you get to the entire proposition. So, okay, let's kind of do this with one more example. And this time it's going to, I think, have an order 3 subformula. So let's just right away list, okay, so there's the order 0. So maybe I'll say ord 0, ord 1, ord 2, ord 3. And so the order 0 are just the variables. That's P, Q, R. Then there's the order 1. So negation P, that's going to be in order 1. Then there's Q conjunction R. That's another order, conjunction. So order 1. And that's all the order 1s, right? So Q is an order 0. So that would not be any of the orders so far. Next, let's get the order 2. Now, this is order 1. This is order 0. So this is, a demonstration of why it's important to compute the order by taking the max, right? This time, you don't add them, or you don't just pick one or whatever. You have to take the max. So the max between 0 and 1 is 1, and then add 1 extra for that symbol, and you get order 2. So this sub-formula here, that is an order 2 sub-formula. So that's negation P O plus Q. Parentheses don't really matter, but I'll just leave it. And then, before moving on, maybe we want to just wonder, what is the order of the overall proposition? Well, this is order 2. This is order 1, as we've already said. So if this is 2 and 1, you take the max. The max between them is 2. And then for the entire proposition, the order is 3, 1 bigger. So that's an order 3 proposition. And that covers everything, right? That's all the sub-formulas. And so here they are. Now that we know what the sub-formulas are and what their orders are, we can go ahead and start making the truth table. So here I've given it the appropriate rows and columns. So it's got 8 rows, and I have put the order 1 sub-formulas in the next couple columns, and then I've put the order 2 sub-formula in the following column, and then the final order 3 sub-formula in the final column. That sub-formula is really the whole proposition, but in any case. Okay, so let's fill some truth values. Half true, half false, and then a quarter and a quarter and a quarter and a quarter, and an eighth and an eighth and an eighth. Okay. Now we want to compute the negation. We've actually already computed that, so I suppose I should not waste time talking that out too much. False in the first 4 rows, true in the others. This one, yeah, okay, I think I must have put in there, but okay. So that is that. Okay, Q and R, so this is a conjunction. Let's apply the conjunction rules. So here we're going to get true and true, so true. On this row, again, always looking at the row or the columns for Q and R, we're going to get true and false is false. So these are the actual values in the table. And I'll just start filling without showing the calculations in any detail, but you get false, false, true, false, false, false. Okay, moving over to the order 2 subformula. Because it is order 2, we have to take this one and look its values up in the appropriate column. We take this one, look up its values in the appropriate column. So I am going to take negation P, which has value false, and O plus it. So maybe I'll just make a little note, F O plus. Q, which is true, and the rule for O plus says that comes out true. Okay. And let's just without so much showing the specific calculations, I'll just start filling in values. So then this is going to come out false. And then this is going to come out false. Actually, might help to show some of the calculations. But anyway, since I don't have a lot of room, I won't do that. But so I'm going to take Q here and negation P here and O plus those. So I'm going to get false. Then I'm going to take Q and negation P and O plus them. I get false. Q, P. So that's going to come out false. And then the last two will come out true. So false, true, true. Okay. And now we come to the final computation, which is going to have me look here for this value, and it's going to have me look here for this value. And we're going to apply the conditional rule. So I'll draw the actual values and the computation on the first row, but after that, maybe not. So what my antecedent is going to be this true value here, t. Consequent is going to be a true value t. So I'm going to get t arrow t, which evaluates to t. Now, let's maybe just come over here and say, okay, everywhere that the antecedent is false, I know that my conditional is going to come out true. So actually, I can just already say true, 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 true. Now, where my antecedent is true, and I come over and look at my consequent, in this case, both of them are false. That tells me that I'm going to get true, arrow, false, and those, if you check your truth table for the conditional, are rows where you get false. And there you have it. So this is the truth table for the proposition. Now, since we've done a couple exercises, we could go ahead and state the sort of rigorous formulation for what the order of a subformula is. And so here you have it. We take all propositional variables to have order 0. That's just by definition, right? That's what order 0 means. Now, if you have a negation, right? So if your proposition is alpha, but alpha is really the negation of some other subformula beta, right? Then we're gonna say what the order of alpha is using what we already know the order of beta is. So let's say that beta is some order n subformula. Then the order of alpha is n plus 1. So effectively just saying, you know, if you ever have a negated proposition, find the order of the subformula and then add 1. And then if you have a conjunction, so if alpha is beta conjunction gamma, so you have two subformulas now, beta and gamma, then find the order of betas, right? You know, continuing in a similar process, find the order of gamma. So let's say that they have orders m and n. Then, as I've mentioned a few times, the way that we get the new order, right, the order of alpha, is to take the max of m and n and add 1. That's the order of the bigger formula. The same rule holds for all the other operations. And now we can start stating some exercises. So here is an example proposition, and your task is to identify every subformula of order 2. Now, in this exercise, we're going to look at a particular proposition, P conjunction Q. Well, what I should explain is that this is the way that you enter into Wolfram alpha, P and Q XOR R. And so if you enter that into Wolfram alpha, so you go to Wolfram alpha, the website, you put that into the bar, and what it will give you back is a bunch of information but so it'll like reformat your input just to show you other ways that it can be written. But then the part that we're going to find most useful is the truth table that it shows you down here. Now, it does not show you the intermediate steps of calculation, and that your exercise here is to actually perform the calculation, right? Get the truth table using the methods we've seen here and in the book, but then to take your answer and confirm that your end result is the same as what Wolfram Alpha gives. And the point of this exercise is that once you see how to do this, you can, in general, just write down any proposition, do the truth table for exercise, and then check your answer by entering it into Wolfram Alpha. So you should be able to give yourself exercises on truth tables until you feel that you can produce the truth table of any proposition. And so this is just writing out what I've just said. And here I encourage you in exercise number 3 to do exactly what I suggested. Now I'm giving you here an example proposition that you could use if you wanted to. And so, go through the procedure, find its truth table, then enter its corresponding expression into Wolfram Alpha and check your answer. But I'm not going to give a solution to this one in my solution video because you can check your own answers using this tool. And finally, I'd like to end with an invitation to ask questions. If anything in this video was confusing, or if anything in the corresponding portions of the textbook were confusing, feel free to ask a very precise question in the comments, and if I can address it in the comments, I will. Or otherwise, I may make a video and insert it into the playlist.